In the 1870s, James Clerk Maxwell had derived the speed of an electromagnetic wave, and he found that the speed of an electromagnetic wave is 1 over the square root of mu sub naught epsilon sub naught. Mu sub naught is the permeability of free space, and epsilon sub naught is the permittivity of free space. And what these constants represent is how a medium, or in this case, how space is affected by an electric wave and a magnetic wave, or an electric field and a magnetic field. So they had values, they had been found experimentally already. So mu sub naught is equal to 4 pi times 10 to the negative 7th Tesla meters per ampere. And epsilon sub naught is equal to 8.85 times 10 to the negative 12th Coulomb squared per Newton meter squared. Now, when you actually go through the calculations, you come out with a value for the speed of light, which is around 300 million meters per second, which is really close to the experimental value for the speed of light. So, if that is the case, then did he derive, is light an electromagnetic wave? Well, it was generally considered to be yes, because it came so close to the value of the speed of light, and so there was not much debate there. But the issue is, some people looked at this and they said, wait a second, there's something missing. Because whenever you talk about the speed of an object, generally it's always relative to something. Even though you're driving down the highway at 50 miles per hour, it's understood to be relative to the ground. But if there's a police car right behind you and you're doing 50 miles per hour and he's doing 50 miles per hour, you are traveling the exact same speed as the police officer. So relative to the police officer, you're traveling 0 meters per second or miles per hour. Relative to the ground, you're traveling, I think I just said 50 miles per hour. So speed depends upon the observer. But there's nothing in this equation that indicates an observer. So this became an issue, and there's a physicist by the name of Lorentz who then spent the next several decades trying to figure out where it was missing. Why is it that it doesn't show up here? In early 1900s, a guy named Albert Einstein came along and he said, well, suppose the speed of light doesn't depend upon the observer, that the speed of light is constant. What are the implications for that? And so Einstein came up with a little thought experiment. And so imagine we'll call this the lab frame. And so he imagine a box here that's moving along at some speed v. This is a mirrored ceiling. And so as light is, and there's basically going to be a beam of light that is shot upwards relative to the box. So in the box frame, it's being shot up, it hits the ceiling and comes back. Let this distance here be h, and that distance is the same regardless of the groups. And so we have these two situations here. Now in this situation, because there's this horizontal component to it, the light is going to shoot up there and then it's going to come back and it's going to get right into the box again. So in the lab frame, you're going to see the light go up and back, but in the box frame, it's going to go up and back. So the question is, what is the implication? Well, we know that distance is equal to speed times time, assuming that there's no acceleration, which we are assuming here. The distance is speed times time. Well, this clearly is going a different distance than this is. This is going the distance of 2h, and this is going a distance of, well, we've got some right triangles here, and we'll do the calculation in just a moment. So therefore, if the speed is the same as we're claiming, and the distance is different, then the time must be different. And so one of the implications is that time is not the same for everything. So let's actually go through the math now. So in this particular situation, why don't we call this time t and call this time t sub p. So we know that v, we can now be more specific. We're talking about the light traveling, ct. And so let's take a look at that triangle there. This distance is h. This distance right here is 1/2 vt. Since the box is in the amount of time t, it's going to travel the distance vt. Therefore, the length here is the square root of h squared plus 1/2 vt squared. And so the total distance traveled is 2 times that. So we have 2 times the square root of h squared plus 1/2 vt squared. That's the distance divided by the time is equal to the speed. And then from this over here, it's a lot easier. I know that the speed is equal to the distance traveled, which is 2h over time, over t sub p. So what we're going to do is solve for h in this equation and then plug it into that equation. So from here, I know that h is equal to 1/2 ct sub p. I'm using p specifically for a reason. At the end, hopefully I'll remember to reveal it. I'm going to take that and now plug in for this. So I have 2 times the square root of h squared. So much for substitution there. 1/2 ctp squared plus 1/2 vt squared over t is equal to c. I have a 1/2 squared here and a 1/2 squared here. I'm going to factor that out. So bring it over here. We have 2 times the square root of 1/4 times the square root of ctp squared plus vt squared over t. That is equal to 1. And then if I square both sides, it's multiplied by t and square. We're going to do both at the same time. So we're multiplying both sides by t, and then we are going to square it. So I end up with ctp, c squared tp squared plus v squared t squared is equal to c squared t squared. Now ultimately what I want to get out of this is I want a relationship between the times, and so I am going to solve for t here. So I'm going to write that last equation again. So this is c squared tp squared plus v squared t squared equals c squared t squared. That's the last equation that we stopped with. Just flash that up one more time. That's what we have right there. And then rewrote it. I'm solving for t, so I want to get this over to the other side. So I have c squared tp squared is equal to c squared t squared minus v squared t squared. Factor the t out, so I have c squared minus v squared times t squared. I want to isolate t, so I divide by c squared minus v squared. So I'm left with c squared tp squared over c squared minus v squared equals t squared, because that and that cancel. So to get into more familiar form, I'm going to multiply top and bottom by 1 over c squared. And so I have t squared equals tp squared on top, and on the bottom 1 minus v squared over c squared. And then in the final familiar form, t equals tp over the square root of 1 minus v squared over c squared. That is the relationship between the two. So what are the implications? A couple bits of notation. This v squared over c, this v over c shows up so much in relativity. It's given a special symbol, and this is a beta. And so it's basically how fast you're going relative to the speed of light. So if beta is 0.5, that means your speed is half the speed of light. And then this 1 over the square root of 1 minus v squared over c squared, which is 1 over the square root of 1 minus beta squared, also has a special symbol. This is known as the Lorentz transformation factor, and it goes by gamma. So we can rewrite our equation here as t is equal to gamma tp. So tp here is known as proper time. And in other words, in the reference frame where in the reference frame of non-movement, that's proper. So proper mass would be the mass of an object that's not moving relative to the observer. In this case right here, we had proper time was the time in which the box was not moving, and then the other one is considered not proper. So if beta is 0.5, then, yep, that shows up. Then if beta is 0.5, I do 0.5 squared negative 1 plus, so that's the denominator. Then I do the square root, take 1 over it, and I get that. So if beta is 0.5, then gamma equals 1.155. Let's do a couple more. If beta is 0.9, notice it is unitless here because we're dividing a speed divided by a specific speed here. We end up with no units here. Gamma equally so. This gamma, since beta is unitless, 1 is unitless. So this is unitless numbers, unitless. We end up with something that's unitless. So at 0.9, so gamma would be the square root 1 over the square root of 1 minus 0.9 squared. So 0.9 squared, make it negative, add 1 to it, take the square root and take the reciprocal, and we end up with 2.2946. Do 0.99. And so 0.99 squared negative 1 plus square root reciprocal. And we get 7.089, if I read that right, yeah. All right, so this gives you some relative factors here. So what does this mean? That means that if I'm in a rocket ship going at 0.99 times the speed of light, do it this way. So v is equal to 0.99 times the speed of light, or I could have just written beta equals 0.99. Then if we have Earth sitting back here, part of the assumption here is that there is no absolute reference frame. If light travels always the speed of light, there is no frame which is going at basically 0 meters per second. So there was indeed at some point a theory that this worked. Then there was a famous experiment in 1890, somewhere around there, by Michelson and Morley, where they actually came up with sort of what's now considered to be the definitive evidence. It was not exactly believed. I still have, even though that was in the 1890s, I have a textbook from the 1930s which still talks about the fact that there is a reference frame. And this, if you hear references to ether, which is not the same ether that knocks you out, this is ether as an ethereal. This was considered to be the substance in outer space which allowed electromagnetic waves to travel. And it turns out that electromagnetic waves don't need a medium to travel. So anyway, what this is deriving right here is known as time dilation. And pause, stop it there.